Sample exam 6. 1 through 14. Number 1, we're given a differential equation dy dx, x squared y plus y squared x all over 3x plus y. Right. So, with that differential equation, the question says the slope field for this differential equation will have horizontal segments when, ultimately, the answer to that is when the derivative equals 0. True? So ultimately, when can the derivative equal 0? Ultimately, when the top equals 0. So ultimately, if we say x squared y plus y squared plus x, or y squared times x, that is, equals 0, then anytime that were to equal 0, we should get a 0 slope, if you will, right? So we'd have horizontal tangents. And with that, if we were to solve this, ultimately putting a 0 in for x is going to give us 0. Putting a 0 in for y is going to give us 0. And keep in mind, if I put a 0 in for x here, that doesn't make the bottom 0 or anything. 0 in for y doesn't necessarily make the bottom 0. Okay? So ultimately, 0 and 0 would be our two candidates. Okay? X equals 0 and y equals 0. But the question is there any other way that we could have this business right here equal 0? So ultimately, if you look at the candidates you have here, one of the candidates they pose here is that y is equal to negative x. Okay. What if y did equal negative x? We'd have x squared, negative x, and then we'd have negative x all squared times x. We plugged in a negative x for y, which would ultimately give us negative x cubed here, and that would be squared, would be plus x cubed. Wouldn't that also give us a 0? So therefore, y equals negative x then would be another candidate, or the top would be 0. And the only other option they gave us was, negative 3x. We could try negative 3x in there and see if that works. We already know that 0 and 0 make it true, so the negative 3x is fairly irrelevant at this point. So it's not bother, but so ultimately it would be those three. So letter E. A-B problem. Ultimately, I guess it's a slope field problem, I guess, but bottom line is it's a derivative problem, isn't it? So all right, what else in the 1 through 5 part? Yeah. And 3, we got particle moves in a plane xy, so that any time the coordinates are x equals alpha cosine beta t, and y equals alpha sine beta t. Okay. And it says the y component of the acceleration vector of the particle at any time is given by the following. And ultimately, keep in mind again, this is our position. These are the location coordinates, if you will. So the velocity coordinates, and again, keep in mind we can write that as a vector by just putting these two comma each other. And then the velocity vector, if you will, is going to be the derivative of these. So we'd have negative alpha sine beta t. And keep in mind we have to multiply by the derivative of beta t, which is beta. So we'd ultimately have alpha beta out here, right? And then the other one is going to be, derivative of this would be alpha beta cosine beta t. So that would be ultimately our velocity. And then our acceleration, if we did that again, we differentiate it again, we get negative alpha beta squared cosine beta t. So ultimately we have that as a constant. Derivative would be negative cosine beta t times beta. And hence we'd have a beta squared out in front, multiplying by another beta. And this one, the derivative is going to be negative, and it's going to be alpha beta squared sine beta t. Alright, and so they want to know what about the y coordinate, I believe, right? Y component of the acceleration, so it should be this one. You have that as an option. Ultimately, this particular expression is not an option, right? But if you look at the options given, you notice that there is a beta squared. There are two other beta squared options, which are a and b, right? And ultimately, that and that together are, if I have alpha sine beta t, isn't that my y right there? So with that said, I'd have negative beta squared y, which corresponds with letter A, I guess. All right, questions on any part of that one? It's a BC problem because it's dealing with vector manipulation. Most of the actual calculus, though, is AB stuff, but the fact that it's a vector issue makes it BC. What else? Through 5. And 2 looks like an integration by parts problem. You got from 0 to 2 of x e to the x dx. It's not a known derivative. Substitution doesn't do us any good. So ultimately, integration by parts should be our next option here, which means that we'll let our u be x and our du be, or dv I should say, be e to the x. Du then would be dx. V would be e to the x. Alright, and e to the x dx, right? So if we do our uv would be x e to the x minus v du would be e to the x dx. And conveniently, e to the x dx is an integral that we can handle without too much trouble. So x e to the x minus e to the x plus c. Alright, and actually it's a definite integral, I forgot. So ultimately, we don't need the plus c. We can just put in our 0 and 2 at this point. Put in 2 there, we're going to have 2e squared minus e to the 2. And then we're going to have in the other parentheses 0 minus e to the 0, which is 1. Yes, because ultimately, remember, this is the answer to this integral right now. Okay? And the whole thing when we get done is the actual antiderivative. So yes, definitely. Okay. So that's why we don't do anything with this in terms of the definite part, because that's going to get taken care of when we have the whole antiderivative and we're finally done with that. So ultimately that'd be 2 just be e squared minus plus 1, which looks like letter C. And that's also a BC problem because it's integration by parts. Any questions on that one? Alright. Others? 5? 6 to 10? Yeah. 6. Okay, at 6 we have a picture of a couple of piecewise functions here, f and g, and it says that the graphs are shown, and we know that this new function h is just the composition of f and g. And so ultimately we want to know h prime at negative 3. Well, in order to know h prime at negative 3, we need to know h prime in general. So h prime in general, when I have a composition, is the outside function evaluated at the inside function times the derivative of the inside function, which is what rule? Chain rule. So we need to figure out what h prime is, and then if we want to do h prime at negative 3, then we need f prime at g of negative 3 times g prime at negative 3. So working our way inside out here, let's figure out this part first. What is g of negative 3? Well, we have a picture of g right in front of us, and it looks like g of negative 3 is 1. Would you agree? So that means we want f prime at 1 then, times g prime at negative 3. And so now we just need a couple of derivatives here. So if we look at f, the f function at 1, it's going down. fact, the slope is down 1 over 3. Negative 1/3 for that f function. Be the derivative of f at 1. Again, the g function at negative 3. If we go over to negative 3, the g function's derivative is, looks like that one's going down also, right? That one's going down at a rate of 1 over 1 though. So that'd be negative 1. So therefore our answer would be 1/3. Which corresponds to letter D. So ultimately that's just a A-B problem, it's definition of chain rule. Questions on that one? Next. Les? From 0 to 3 of the x over x squared plus 16 square root function. Ultimately, it doesn't look like a known derivative, but if we did our u substitution here, should be the first thing to come in mind because our du would be related to what we have left over that's not u. So if we substitute, we're going to get radical u on the bottom. And then our x dx, instead of x dx though, we have 2x dx. So if we just divide it by 2 on both sides, we could get our x dx. So put in a half, we get a half here and du here. And if we anti-differentiate u to the negative 1/2, we get u to the positive 1/2 divided by a half. So it'd be 2 radical u in other words. Which ultimately will give us 2 radical x squared plus 16 on 0 to 3. And conveniently 3 in there gives us 9, which gives us 25. So we'd have in our first part 2 times 5, which would be 10. So plugging a 3 in here would give us 10 inside. Plugging a 0 in there would give us 2 times 4, gives us 8. So we'd have half times 2, which would be 1. And looks like that would correspond with letter A. So that is an A-B problem, just use substitution. Questions on that one? Next, 69, Kyle? Let's see, on C number 7 we got sequence 3 to the n plus 1, 4 to the n. And the issue here is what is the value of this function, or this series, as n approaches infinity? Can we come up with a value, or does it diverge? Notice that diverge is an option here. What we want to recognize here is that if we manipulate this integrand, we could write it as 3 to the n times 3, couldn't we? Which would allow us to write that, and which would also allow us to write 3 times 3/4 to the n. Which ultimately that makes it what? Geometric. True. And the r value is less than 1, so it does in fact converge. And we know that it converges to a over 1 minus r. So a being our first term here, if we were to put a 1 into the argument here, we get 3 to the 2 and then 4 to the 1. Would be 9/4 would be our a value. And then 1 minus negative, or 1 minus 3/4 would be our r value. So ultimately we have 9/4 divided by 1/4. 9/4 times 4 over 1 ultimately give us 9. It's like letter C. Questions on that one? Others, up to 10? Sure. Anybody else, up to 10? 10 looks like an integration by parts, or not integration by parts, but partial fractions, because you got 1 over something that looks like it can be factored. And we know that u substitution isn't going to work here because there's no 2x part to this or anything. So if it's integration by parts, we get our two factors, x plus 2 and x plus 3, our a and our b. Should have done that first, hopefully. And that means that a times x plus 3 plus b times x plus 2 has to equal the top of the result. Which, keep in mind, we're working backwards from the result. So we need that top to equal 1. So that means ax plus bx plus 3a plus 2b is equal 1. So a plus b times x plus 3a plus 2b is equal 1. And the system, the AB system that we can make out of that is that fact that a plus b has to equal 0 because there is no x term on the right. And 3a plus 2b equals 1. So we can either substitute or we can eliminate. It's up to you. I'd probably eliminate here, go -3, -3, and -3. Adding a's would be gone. We'd have -b here. We'd have negative, or positive 1 here, I should say. -3 times 0 is still 0. So if negative b is equal to 1, then b would be -1. And therefore a would be 1. Because we get, again, that a plus b has to equal 0. Question so far? Alright, so once we know that, we know that 1 over x plus 2, and ultimately minus 1 over x plus 3, putting a -1 in for b. And if we integrate those two separately, we're going to get natural log of x plus 2, absolute value of course, minus natural log of x plus 3. Keep in mind this is a definite integral, we're going from -1 to 1. So if we plug in our 1 into that, we're going to get ln 3 minus ln 4. Minus, if I put a -1 in there, we're going to get ln 1 minus ln 2. Keeping in mind ln 1 is 0, so we're ultimately going to get ln 3 minus ln 4 plus ln 2. And here's a good issue of making sure we know how to handle pre-calc problems, because this is certainly not a pre-calc problem, but changing this into the right form is we know that when we have a subtraction of logarithms that could come from a quotient. We can break up quotients by subtracting the two top and bottom logarithms, as long as we have the same base, which we clearly do. And same thing with the multiplication of two logarithms, we can put that back in as a product and we get 3/2. And that corresponds to letter A, I believe. That's correct. So all in all, it's a BC problem because it's partial fractions. Like I said, there's a pretty good element of pre-calc work too. Questions on number 10. Alright, what else? Okay, number 9, we have ln of 3x plus 5 is our equation, and we want to find the second derivative. So let's see what happens when we set out to find the first derivative here. We got 1 over 3x plus 5 times 3. It's 1 over the argument times the derivative of the argument. We have a natural log. So that'll be 3 over 3x plus 5. And second derivative, I would probably rewrite this as 3 times 3x plus 5 to the -1. That way I can just use the chain rule to find the second derivative. So my d squared y dx squared should have been -3, 3x plus 5 to the -2 times 3, the derivative of the inside again. So on top we'd have -9, bottom we'd have 3x plus 5 all squared. And it looks like that corresponds to letter D. So AB problems, finding second derivative. Okay, last part, 11 through 14. Right? 11, we got a, looks like an implicit differentiation problem because we got something that is not solved for x, and we want to know the derivative at a point. So if we find the derivative, 2y dy dx should be our first part here. And then what we have to recognize here is that we have a product between these two. So if we do our product rule, first times the derivative of the second, plus the second times the derivative of the first. And on the right hand side, the derivative of 21 is 0. Alright, so again, the first, keeping in mind that I'll just keep the negative out in front here. That way I don't have to worry about that being a negative 2x. I can just treat the 2x y as if it's its own part. So minus, again, first times the derivative of the second, plus the second y times the derivative of the first, which is 2. And we'll have 2y dy dx minus 2x dy dx. Minus 2y here equals 0. And if we get the 2y on the other side, and then factor out the dy dx, we should have 2y minus 2x here. Alright, and with that, we want to know the derivative at a particular point. And that point is negative 3 for y, 2 for x. So we should have negative 6 on top. Negative 6 minus 4 would be negative 10. So we get 3/5. Corresponds with letter E. So AB is going to be implicit differentiation. Questions on number 11? What else? Jake? 12, we got the average value of radical 3x on 0 to 9. So remember, the average value of any function is the integral from 0 to 9 of our function, the area under the curve, divided by the length of the interval. So 1 over b minus a times the integral from a to b of f of x dx. So ultimately we'd have a 1/9 out here, and if we anti-differentiate with our 3x to the 1/2, if you need to use u substitution here, you can with the 3 here, otherwise you can pretty likely can just do it in your head, making sure you consider the chain rule here, but it doesn't hurt to do the substitution though, just to make sure. So ultimately we'd have u to the 1/2, and then 1/3 du. And ultimately that would be u to the 3/2 divided by 3/2, or times 2/3 times a third. Right? And then from there, put our 3x back in. And then we can evaluate it on 0 and 9. So if we put a 9 in here, we're going to get 27. 27 to 3/2 is going to be, actually, yeah, it's going to be a radical. Okay, that's fine. Looked at the answers, they're radical answers, so I guess it makes sense that it should be a radical. So bottom line here is if we got 27 in here, if we go radical 27, keep in mind we'd have radical 27, and we'd be raising that to the 3rd power. The root is 2 is the root, 3 is the power, and so ultimately cubing that would give us radical 27 times radical 27 would give us 27, times another radical 27 would give us 27 radical 27. So on top we'd have 54 radical 27 over 3. We evaluated that. Nicely for us though, the 0 is going to give us 0, so we don't have to do that again. We just got the one element to deal with here. 54 here divided by 3, 54 divided by 3 is 18. And then we have 1/3, so it would be 6 radical 27. Alright.
On the outside of your integral.
Right, this is just the integral part right here, right? Yeah. Because we took the 1/3 out because of the substitution part. So this right here, keep in mind this is just the area that we're finding first. We'll go back and put it up here in a minute. The The only other issue here though is that 27 has a perfect square factor. We can simplify that. We made it into 9 and 3. Then ultimately I'd have 18 radical 3. So again, that part right there would be the area under the curve, if you will. And so the average value though is going to be that area under the curve times 1/9. So we get 2 radical 3. Would be letter B. And ultimately that would be a AV problem. So average value would use substitution. Any questions on any part of that one that I did? What else? Oh. 13 or 14? Let's see, 14 we have the negative infinity to infinity of e to the opposite of absolute value of x dx. Okay. Ultimately this is an improper integral because it has infinite limits here. And so with that, what we want to try to figure out is can we get an answer for this? And if so, what is it? If not, it could be very well be divergent, but we'll find out. So ultimately, what we want to do when we have a negative infinity to infinity situation, if we split that up into two integrals, if we go from negative infinity to 0, let's say, and we do e to the negative absolute value of x dx, and then we do another one from 0 to infinity of e to the negative absolute value of x dx. Now, here's what I want you to think of. Now that we split it up like that, remember the way we do it properly is we write limit statements. We write the limit as a approaches negative infinity. And we go from a to 0 of e to the negative absolute value of x dx. And then we go from, oops, got my limit. So then we write from there limit as b approaches infinity of 0 to b, e to the negative absolute value of x dx. Alright, so that's how we want to split it up in order to get two integrals that are possible to evaluate. We may or may not be able to evaluate them, but that's how we want to set it up in any case, no matter what the integrand is. Alright, and let's see if we can come up with an answer here. Well, let's think about, we don't know an antiderivative necessarily for e to the negative absolute value of x. However, think about if I were to put, anything that, this is going from a negative infinity to 0, so whatever I put into this is going to be a negative, and it's going to become, my x, any x I put in here is going to be negative, it's going to become positive, but then I'm going to make it negative again. So the question is then how this function e to the negative absolute value of x, isn't it going to behave like e to the negative x then? On that interval? Alright, because again we're going to put, the values we're putting in here are going to be negative numbers. Like if I put a negative 5 in there, for instance, I'd get 5, and I'd make it negative. It'd be e to the negative 5 would be the y value. True? Okay. And so ultimately this is going to behave just like e to the negative x does. Okay. Right. And so if we evaluate here, we're going to get negative e to the negative x is going to be our antiderivative on a and 0. And if we put a 0 in there, we're going to get negative 1. This e to the negative 0 is going to be negative 1. Negative e to the negative 0, that is. And then as if I let a go to negative infinity here, I'm going to have negative infinity. I'm going to put negative infinity in here. It's going to be actually e to the infinity. Actually, I think I want that to be the opposite of what I said the first time. Let me go back to this part here again. Ultimately, think about this. If I made, that'll be easier to think of. If I made an XY chart for this function, okay, so, and I put on the negative side of it, if I put in a negative 5 here, I'd get e to the negative 5. True? All right. And so, it's negative 5 here, negative 5, and so if I just had straight up e to the x, actually this would behave like e to the positive x. I said that backwards. Okay. Think about why. If I put negative 5 into e to the x, I'd get e to the negative 5, wouldn't I? And that's what I want. I want these two to mirror each other. I want these two to have the same xy chart, otherwise not the same function. So this is actually a positive x. So, which is good because at negative infinity, e at negative infinity is going to go to 0. Okay, and so we'll get that as our result. Alright, so let's see what we can do next with that. Make sure I have this part right. This is actually going to be positive then, isn't it? It's a positive 1. Because this was e to the x in the original part, so there's no negative out here either because of the chain rule. Alright, so anyway, back to that. Again, this function behaves like e to the x, then it's going to be ultimately 1 as the answer. And then if we do it on the positive side here, okay, what is this function going to behave like if I put a positive 5 in here, let's say, into e to the negative absolute value of x? If I made an xy chart for that, if I put in 5, I'm going to get e to the negative 5. And so this function is going to behave like e to the negative x. Agreed? Because the chart for this one, if I put in a 5, I'd get e to the negative 5. Again, just an example to make sure we understand what this function is going to behave like. So on the left side, the function is going to behave like e to the x. On the right side, the function is going to behave like e to the negative x. And then ultimately, that same work that we did up here, we're going to wind up with what we had the first time. I had that backwards. And we're going to go 0 to b. The b part's going to be 0 because we're putting infinity in here. So e to the negative infinity is 0. And then we're going to be putting in minus. And then e to the 0 here would be negative 1. So we wind up with 1 again. And ultimately, you had these two both equal 1, so therefore the total is 2. So we did a little bit of thinking about the fact that how this function is going to behave, because again, we don't have an actual antiderivative of that function that we know. But ultimately, the absolute value, if you think carefully about what's going to happen with the values that we're given, okay, then this function is not going to behave any different than e to the x does on the left side. And on this side on the right, it's going to behave like e to the negative x, which are both integrable, and we can find both answers and add them together, and we're good to go. What else? Sample exam 6. There. Let's see, 13. We have a piecewise function that says that here that g of x is negative 1 to x of f of t dt. And it says which of the following is true. And they ask us about some values here. G of negative 4, keep in mind, would be the integral from negative 1 to negative 4 of f of t dt. And since it's a triangle, we could actually calculate that if we go from negative 1 to negative 4, and we draw down to 2 to negative 1 would be 3. Be a 3 by 3 triangle we get there. Okay. However, we got to be careful here though, because remember the triangle, we're not just doing the triangle because the triangle goes above and below the x-axis. Okay. So really what we'd want is we'd want the 2 by 2 triangle that goes from negative 3 to negative 1. Okay. And that 2 by 2 triangle, of course, would have a area of 2. So keeping in mind that we're going 1, 2, 3, 4, got negative 1, 0, 1, 2. And so, again, that area right there that we're looking at here would be 2. And this area right here is a 1 by 1 triangle, so that would be a half. Now, keep in mind also that we have to be careful with the fact that we're going backwards here. So that means even though this is above the x-axis, it gets counted as what? Counted negative. So actually it's going to be negative 2 plus a half. The negative half would get counted as a positive. So therefore, what would g of negative 4 be? It'd be negative 3 halves. Okay. Alright, and then g of negative 1 would be the area from negative 1 to negative 1 of f of t dt. And we know that answer is, of course, 0. And in part A, that says that g of negative 4 is equal to g of negative 1. Well, that's clearly not the case. So it's not letter A as our correct choice. Then they ask us about the 3's. What about g of negative 3? If I do negative 1 to negative 3 of f of t dt, that answer would be negative 2 then, wouldn't it? It'd be that triangle again, but going left it would be negative 2. And then g of 3, if I go from negative 1 to 3 of f of t dt, going all the way over here to 3, we got 1 here. This would be another 2 by 2 triangle, so that would be a 2. This triangle over here would also be 2 by 2, so that would be 2 as well. So the areas, got 2 here, 2 here. If I go from negative 1 over to 3, that would give me a positive 2, negative 2. This one would equal 0 then, wouldn't it? So therefore, neither one of those are equal, like it says there. And then it says g of negative 1 and then g of 3. What about g of negative 1 and g of 3? Yeah, those are equal, aren't they? So therefore, it should be letter C. It'd be a B problem. I guess ultimately it'd be a. I guess that would be a area function problem. Anything else on sample exam 6, 1 through 14? Anything we missed or anything you want to go back to?